Hello everyone, so welcome. Now we are going to learn about Heisenberg's uncertainty principle. So the two very important experimental findings before the pronouncement of the Heisenberg's uncertainty principle were Davison-Germer experiment and double-slit experiment. So what did they show? They show that particles actually are depicting the interference pattern, which means wave nature of particle exists. Note that particle is localized at exact position, but the wave is spreaded. Okay. So when you will note that in from the experimental finding, the particle will go to the single point only. But when you check for the wave nature, okay, you will find that it is spreaded, and we can also verify it mathematically from the probabilistic information. Also in Davison-Germer experiment, the individual electrons are impossible to be traced exactly. Such uncertainty about particle was never found in the classical physics. Like in classical physics, we know things exactly. Okay, we just apply the equation of motion. We find at what time and at what position the particle would arrive from position A to position B. Okay, but in the Davison-Germer experiment, we cannot predict that where the electron would go. Okay, but if you repeat the experiment sufficient number of times, repeated experiment show the real nature. So such experiments actually inspired Heisenberg to propound the uncertainty principle. He said that okay, things are not very certain in the aforesaid experiment. That means there should be some kind of uncertainty in the laws of physics. And he said that momentum and position of particle can't be. The word here is can't be. They cannot be exactly established and simultaneously with full accuracy. Okay, there are some minute typographical error in the handwriting, so I am correcting it. So he said that momentum and position of particle can't be exactly established and simultaneously with full accuracy, and they are actually inversely proportional. For example, if you try to find the uncertainty in momentum, it is inversely proportional to the uncertainty in position, or vice versa. Okay, so we could write that product of uncertainty in position in x direction multiplied by uncertainty in momentum in x direction, okay, is actually equal to or greater than the quantity h bar by 2, and h bar by is nothing but Planck's constant divided by 2 pi. So it has the mathematical value of 1.054 multiplied by 10 to the power minus 34 joule second. So in the same way, you could define the uncertainty relation for some other quantities also, and this is the uncertainty relation for energy and time, and this is the uncertainty relation for angular momentum and angular position. For time and energy, it says that the uncertainty in time, energy, and multiplied with uncertainty in time is greater than or equal to h bar by 2. In the similar fashion, the uncertainty in the angular momentum multiplied with the uncertainty in angular position is greater than or equal to h bar by 2. Now, Heisenberg's uncertainty principle could also be found from the de-Broglie concept. We know that de-Broglie hypothesis that every particle do have the wave counterpart associated with it, which is actually h by momentum. Okay, h is Planck's constant. So according to de-Broglie hypothesis, we know that group velocity of any wave particle is actually equal to the particle's velocity. Why that? Because a particle is thought to be the packet of various waves, that is, it is group of the wave. Okay, particle is thought to be made of many wave packets. Many wave packets, hence we call it group of wave. So that is why we say that the particle's velocity is equal to the group velocity. Now let us we have two wave group which two waves which makes a wave group. The first one is defined by psi1, the second one is defined by psi2, and it is a cos omega 1t minus k1x multiplied by a cos omega 2t minus k2x. Okay. The resultant displacement of the above two would be simply when we add that, and we pretty much know how to add the trigonometric function. It is in the form of cos A plus cos B. Okay, so when you put that formula using the cos A plus cos B, we find that it is going to be 2a cos omega t minus kx multiplied by omega delta omega t by 2 minus delta k by 2 into x, where omega is nothing but omega 1 plus omega 2 by 2 and k is k1 plus k2 by 2, and delta omega is omega 1 minus omega 2 and delta k is k1 minus k2. And when you find the velocity of resultant wave, it is simply delta omega by delta k. This is the way the velocity of any wave is defined. Okay, we know it from the basic nature of the wave equation, and when you apply the limit, it becomes delta omega by delta k. So this is the particle's velocity as well, because we know it from the de-Broglie hypothesis. It says that. So here we have the same equation, that is 2a cos omega t minus kx multiplied by cos delta omega t by 2 minus delta k by 2, and it is going to be x. Okay, this is basic writing mistake. So these waves have the linear spread of delta x. That means the particle could be found anywhere in the delta x, and this is what we call the uncertainty. Okay, so because of this delta k, the x is also uncertain, the position is uncertain. You cannot predict that to be found at one single place, and this is what we have found uncertainty in mathematical fashion. Now one of the condition of for formulation of wave packet is that this part is going to be 0. Okay, so when this part goes to 0, we get to know that okay, the part inside the bracket should be the odd multiple of pi by 2. Odd multiple of pi by 2, and if x1 and x2 are the two consecutive nodes, then we will have delta 2 equation, equation 1 and equation 2, and first is delta omega by 2 into t minus delta k by 2 into x1, and it is going to be 2n plus 1 multiplied by pi by 2, and another is 2n plus 3 pi by 2. Look, there is a difference of 2, like the way there is a difference between two odd numbers. If one is 1, then another is going to be 3 or 5 or 7 and so on. That is why we have added 2 here in the value. So when you solve that, you actually get to know that delta k by 2 multiplied by delta x is going to be pi. If you bring the pi to the left side, delta k by 2 pi multiplied by delta x is going to be h, and which is nothing but delta p multiplied by delta x into delta h. How did we get this value? Simply use the de-Broglie hypothesis. Lambda is going to be h by p. So when you break lambda, it is going to be 2 pi by k, which is equal to h by p, and bring k to the left side, then it is k is equal to 2 pi p divided by h, and then when you differentiate it, delta k is equal to 2 pi delta p divided by h, and you just put it inside this equation, you get the answer. Okay, and where delta p is obviously error in the momentum observation. So when a group consisting of a large number of waves taken into account, we get this form. Okay, this is the exact form. And there is a more mathematical concept required here, but the basic physical understanding, we are complete with that. Now let us move to the one very important part, that we are going to learn Heisenberg's uncertainty principle from electron diffraction through single slit. This could be asked in examination because similar questions has been asked in the examination hall. So we have monoenergetic beam which are incident on slit of width delta y. So as electrons, beam would behave as wave, that is according to the de-Broglie hypothesis. It would also undergo the diffraction and it will produce the Fraunhofer diffraction pattern. So this is very important, that Fraunhofer diffraction pattern is being produced, and this is pretty much well understood topic everywhere, and you will learn it explicitly in optics and waves, like in waves part of our syllabus. So just remember that for the first minima we have the condition this delta y sine theta which is equal to lambda. In that way you get delta y which is equal to lambda by sine theta, and theta is obviously the spread here. So direction of electron before diffraction and direction of electron after diffraction, we need to know that. So direction of electron before diffraction is obviously along the x-axis, okay, and direction of electron after diffraction will be along two directions, that is OC and OD. So we could write that it is along plus y-axis and x-axis, and then minus y-axis and x-axis, that is line OC and line OD. Hence momentum along y-axis is going to be p sine theta, and momentum along minus y-axis is going to be minus p sine theta. So in that way you could find the uncertainty in momentum in that direction, that is p1 minus p2, and when you calculate it mathematically, it is p sine theta minus p sine theta, that is 2p sine theta, and p is nothing but h by lambda. So you got it 2 sine theta by lambda, and you obviously know that from here 2 sine theta by lambda was nothing but delta y, okay, 1 by delta y. So in that way you could simply write that it is delta y multiplied by delta p is equal to 2h, and this is actually close to our actual concept. Okay, and let me tell you, Heisenberg uncertainty principle is not the mathematical expression, but it is the physical concept. Why I am saying this, we will see it. It is physical concept and not a mathematical expression only. So mathematical expressions is secondary, as a concept it is primary. And what is concept? Concept is that your accuracy could not be same for the both momentum and its position for any particle. Now we are required to do some application of Heisenberg's uncertainty principle. Like let us do one PYQ and the important topic as well. So that is the non-existence of free electrons in nucleus. So the assumption is that free electron can exist in nucleus, and if it is existing in nucleus, the maximum uncertainty is obviously going to be around the diameter of a nucleus. Look, in quantum physics or quantum mechanics, you cannot say anything for sure. You need to have a range for that, and that is what if you try to predict quantum mechanics exactly, it is actually going to convert into the classical physics. Okay, that is the inherent beauty or limitation, whatever you may call it. So diameter of nucleus is double the radius, which is 2 multiplied by 10 to the power minus 14 meter, and 10 to the power minus 14 meter is the general range for that. That means the range for the radius of the nucleus. So when you apply the Heisenberg's uncertainty principle, delta x multiplied by delta px is greater than h bar, and let me tell you, I have not taken h bar by 2. Still, this is correct. Why? Because we are actually right here. Why? Ki whatever is going to be greater than h bar by 2 is also going to be greater than h bar. That means this is also correct. So, as a concept, we are correct here. So, in that way, when you do the basic mathematics involved, like divide h bar by delta x to find delta px, you find that it is 0.5278 multiplied by 10 to the power minus 20 kilogram meter per second, which is the corresponding uncertainty in the momentum. So minimum momentum would be same, because that is the basic theoretical concept we need to learn here, that uncertainty in any quantity q is actually equal to or nearly equal to the quantity itself. Okay, that is the basic assumption in the quantum mechanics. And again, this assumption is because in the quantum mechanics we cannot say anything for sure. Okay, so the corresponding energy, we have got momentum. From the momentum we could get the corresponding relativistic energy. So relativistic energy could be found using this formula, that is E square is equal to P square C square plus rest mass energy whole square. This m naught C square is nothing but rest mass energy. Okay, and when you put these values given here, which we have found the momentum. Yes, we know the momentum. We have the value of rest mass energy of electron as well. The rest mass energy of electron is 0.511 million electron volt. Okay, and this is the value of electron volt in joule. Okay, so we converted it into from electron volt to joule. In that way, we could found that it is 9.875 million electron volt. That is the energy of electron if it is going to stay inside the nucleus. So if we check now that if electron really have that kind of energy or not. Suppose that if electron have this much energy, then we can say that we are correct in assuming that electron is inside the nucleus. But when you try to find it experimentally, the highest value of kinetic energy, which is actually observed from beta particle emission, which is just around 4 million electron volt, which is double less than that. Okay, so if electron is not equipped with such a high energy, then it cannot reside inside nucleus. So that is where we have proved that electron is not existing in the nucleus, and that is our PYQ. Now we could find the same thing for proton, neutron and alpha particle, and because the question has been asked for electron, it could in future be asked for proton, neutron and alpha particle, that whether they are found inside nucleus or not. Okay, so let us solve this, and now we know how to solve this, but still let us do it again for the clarity. So always remember, for any particle to be in nucleus, the uncertainty in position, we know that it is going to be in the order of radius or say diameter, because they are just around same in the order. Okay, not much difference, because we are talking at really very low level, that is something around in the range of 10 to the power minus 14. So order of just 10 to the power minus 1 or minus 2 won't create much difference. So from above information, one may easily find the uncertainty in the momentum by using Heisenberg uncertainty principle. Like if you know delta x, then you know delta px. Okay, and if you know delta px, then you can definitely know energy E. But energy have different expression for the relativistic and non-relativistic case. Relativistic case is when energy is around equal to or more than the rest mass energy, and this is when not the case is not that much. Okay, in another way, the relativistic is where the speed of the particle is around the speed of light, or more than not more than that, but comparable to speed of light. Okay, and non-relativistic case is different from that, like not that simply. So then from uncertainty in momentum, using this formula, one may easily find energy, but this holds good for the relativistic form only. and then we could compare using the energies whether the said particle would be found in nucleus or not. So thus for anything to be inside the nucleus, its uncertainty should be around 10 to the power minus 14. Look, before this we took 2 multiplied by 10 to the power minus 14. But this 10 to the power minus 14 is so small that multiplying some magnitude, some small numbers 1, 2, 3 won't create much difference. So we are correct here too. Okay. And in that way, when you find the uncertainty in momentum, you actually get 5.3 multiplied by 10 to the power minus 21 kilogram meter per second. Hence, this is the minimum momentum because we know that delta P is actually equal to P itself. Okay, we have learned that. And from using this momentum, we could find the velocity of the particle by using this formula. Momentum is mass multiplied by velocity. We will find the velocity, and if the velocity is comparable to the speed of light, like if velocity is somewhere comparable to speed of light, then it is case of relativity, that is relativistic case. We are saying this because when you find the relativistic factor gamma, that is 1 upon 1 minus v square by c square, so this should be very small. Okay, so let us see how. So when you find the velocity using this expression, we have momentum, we have mass for any particle. Like for, let us do it for proton and neutron at first, because they both have nearly same mass. So when we did that, we found the velocity of proton or neutron to be around 3.1 into 10 to the power 6 meter per second. So let us check what is the relativistic factor this. If it is going to be very, very small, that we could neglect that, then our case is non-relativistic, otherwise it is relativistic. Okay, so you can always check that using this expression, that is relativistic factor, 1 minus v square by c square whole under root. Now we could see that the speed of proton and neutron is 1/100th of the speed of light. That means the case is non-relativistic case because it is going to be very, very small. It is just 1 in the 100th part. Okay, so we could simply use the classical formula, that is in the kinetic energy is momentum square divided by 2p. Okay, and in the same way the kinetic energy for proton is actually going to come around 52 kilo electron volt, and similarly kinetic energy for neutron is going to be 52 kilo electron volt because they both have same momentum and same mass here, nearly same. Okay, exactly they are not same, but nearly they are same. So, and they are very less differentiable, so energy could be considered same for them mathematically for us to learn the concept here. So experimentally, energy carried by proton and neutron are much more than the required 52 kilo electron volt, and similarly minimum kinetic energy of the alpha particle is going to be 13 kilo electron volt, which is divided by the 4 because mass of alpha particle is 4 times the mass of proton, so we divide it by 4. So we now have 3 important parts. Let me tell you. The first one is kinetic energy of proton, kinetic energy of neutron, and the energy of kinetic energy of alpha particle. So when you found that actual energy carried by them are way more, okay, not this much, that means they are definitely existing, like electron, neutron and proton are definitely existing inside the nucleus, because this is the minimum requirement, but they have more than this. That means they can stay inside. The same logic which we applied during the electron part. Okay, and for alpha particle, okay, energy of the alpha particle has been experimentally found to be more than the required 13 kilo electron volt, hence all are found within the nucleus. Okay, so in all case we just proved that they could exist inside the nucleus, because for proton the energy, minimum energy is 52 kilo electron volt, for neutron it is 52 kilo electron volt, for it is alpha particle it is 13 kilo electron volt. But for electron and for proton and neutron, even the rest mass energy is way lot than this. Okay, and for alpha particle too, that means they all can exist in the nucleus. This was our main part. So I think in future we could definitely have a question from this section. This is the SPYQ, what I say, the question similar to PYQ, because this is PYQ. You can yourself compare it. Now this is also 1 PYQ. We are going to cover ground state energy for linear harmonic oscillator. Okay, and we also call it 0-point energy. So let a particle executing SHM have mass m. So total energy is obviously kinetic energy plus potential energy. Kinetic energy is p square by 2m and potential energy is half omega square x square. Suppose that the maximum uncertainty in the position be delta x and delta p will be corresponding uncertainty in momentum. So when you apply the Heisenberg's uncertainty principle, that is delta x multiplied by delta p is equal to h bar by 2. So in that way you get delta p is h bar by 2 into delta x, and we know that the momentum is approximately equal to the uncertainty in momentum and position is equal to approximately equal to uncertainty in position. So in that momentum is actually equal to h bar by 2x. Now we do nothing, just take this momentum from here and put it here. What you will get? You will get this expression of energy, that h bar square divided by 8mx square plus half m omega square x. And for ground state, this is very simple. The ground state, the energy should be minimum. So mathematically, you should find the minima. For minima, the differentiation of E with respect to x should be 0. Okay. This is the mathematical condition, class 12 concept. So when you just differentiate it with the x, you actually get x square is equal to h bar by 2m omega. And for minima, the condition is that the double differentiation should be positive. And that is the case when you do the double differentiation of the same thing, you get the value to be positive. So at this position, that is x square is equal to h bar by 2m omega, okay, we will have our ground state energy. So what we do now, put this value in this energy, and whatever the energy comes, that is the ground state energy. You put this value and the result is ground state energy. Okay, so hence at x square is equal to h bar by 2m omega, E would be minimum, and therefore when we substitute this value which I just told you, we get half h bar omega, and this is the minimum energy, which is different from the classical, because in classical form the ground state energy or the minimum energy is 0, but here it is not so. Here we have h bar omega by 2. Okay, so this is the beauty of quantum mechanics. Now in the same way we could do the another PYQ, that is size of the hydrogen atom from HUP, that is Heisenberg's uncertainty principle. So as in hydrogen atom, electron moves around the proton in a circular fashion of radius r, assumed it to be circular for our mathematical easiness. So the maximum uncertainty in position of the electron is actually delta r is r. Okay, we know that. We know it pretty simple, that uncertainty of any quantity q is around equal to the quantity q itself. That is the main idea here in Heisenberg uncertainty principle, main idea. So now the corresponding uncertainty in momentum is just h bar by r, and right now I am just doing fast tracking the mathematics because we have done it earlier a lot of time. So energy of hydrogen atom is simply again kinetic energy plus potential energy, and potential energy of the two charge particle system is charge 1 multiplied by charge 2 divided by 4 pi epsilon 0 distance between them, that is r. So charge 1 is proton, that is positive charge, and charge 2 is electron, that is negative charge. Okay, let me use the same color for a better understanding. Again, what we will do, we will find the momentum and we will put this momentum here in the energy equation, and what we will get this expression for energy, that energy is equal to h bar square divided by 2m r square minus e square divided by 4 pi epsilon 0 r. Okay, and when we need to find the size of the hydrogen atom, so just apply your mind. If you try to find the minimum radius, that could be the approximate size of the hydrogen atom, and for minimum radius we could find the corresponding minimum energy, that is we could find the ground state energy. So if you find the ground state energy, you could actually find the minimum R corresponding to that ground state energy. Okay, because you cannot find the minimum R directly. We have the energy equation. So let us find the energy that is in the ground state. So in that way, we have the expression for dE, dE by dx, that is equal to 0. And when we solve it, okay, we actually get the value of R, that is equal to 4 pi epsilon 0 h bar square divided by me square. And this is pretty simple. We are not doing any mathematics above class 12. We are just differentiating it for any minima. For any minima, the condition is very simple, that suppose that we are finding the minima of fx, then its f derivative x should be 0 and f double derivative of x should be greater than 0. This is the only condition that we need for minima. And we are finding minima for energy because it will give us the minimum value of radius, because that is the ground state energy. So radius should be the lowest. And if we find the radius to be lowest, like in the hydrogen atom there is only one electron, that means we are actually able to find the size of the hydrogen atom. Okay, that is the analogy, beauty of the analogy in the quantum mechanics. So let us do that. Minimum energy is R. Minimum energy for the energy equation, the double differentiation should be greater than 0, and which is true when you find that in rough. So you just need to write which is true. Okay, and thus that means this value, that is R, is equal to 4 pi epsilon 0 h bar square divided by me square is the radius of the electron in the ground state. And when you calculate that, because all the things given here are constant, it comes around 0.529 angstrom, and which will be also the approximate size of the hydrogen atom. Now let us find the ground state energy of electron in the hydrogen atom. So in the last section, what we need to do, we need to just put, this is the value of R. For this R, we will directly go inside the ground state energy of the hydrogen atom. So when you put this value of R in the energy equation, okay, we will directly get the ground state energy of the electron in hydrogen atom. And when you put that, that is R is equal to 0.529 angstrom, m is equal to 9.1 multiplied by 10 to the power 31 kilogram, and the value of charge of electron and h bar, we simply get energy to be minus 13.6 electron volt. Okay, and this one must have understood in the class 11 and 12 as well. Now there is another section, that is broadening of spectral lines. So I feel this could be future PYQ. Future PYQ. Okay, future question in UPSC. So let us call this, as of now it is SPYQ, that is question similar to PYQ. So what is this broadening of spectral lines? So consider an atom in excited state. Suppose that an atom is in excited state. So when this atom de-excite, like when whatever goes to the upper state energy, it always comes back to the lower state. Again, that means de-excitement, and it happens in very short interval of time. And what it does, okay, when you lose energy, you lose the energy in the form of wave. That means you emit a photon. So what will happen? You go to the higher energy E2 from E1, and when it comes back to the E1, so what you will do? You will release the energy with photon, and the frequency of photon would be simply nu. Okay, so such an average amount of time under which the excitement happens is called the lifetime of the state. So let tau be the lifetime of the given excited state, and hence from uncertainty principle we could simply say that delta E multiplied by delta T is equal to h bar. We have learned this, just memorize it. Okay, so we could simply find that energy is h bar by tau, because we know that, again, the same concept, that uncertainty in any quantity is equal to the quantity itself, and we call it natural energy width of the state. Clearly, as per the Heisenberg's uncertainty principle, shorter the lifetime of the excited state, wider the energy gap. Okay. And the corresponding frequency gap, if you know the energy gap, you can always know the frequency gap. That is delta E by H, and it is simply h bar by tau divided by h, and that it is equal to 1 by 2 pi tau, and we call it natural width line. To get an idea in the numerical value, the lifetime of such an atomic state is in the order of 10 to the power minus 8 second. So the difference, that is the uncertainty in the frequency, is with this value. When you put 10 to the power minus 8 in this equation, you actually get 1.67 into 10 to the power 7 hertz, and this is the range for the frequency of such an emission. So that we call broadening of the spectral line, that it become broader. There is a range in now. Broadening is delta nu. Now in the same fashion, we could find the mass of pi meson. So what is pi meson? Let us see. In 1935, Yukawa proposed that the nuclear forces arise through the emission of particles by one of the nucleons and absorption by the other's nucleons. And this particle is actually known as pi meson or pion. And if mass of pion is m, then when it is emitted, the corresponding energy imbalance will be mc square. And if there is energy imbalance, there would be the time imbalance also, as per the Heisenberg's uncertainty principle, and that is h bar by delta E, that is h bar by mc square. And the range covered by pion, because this is the time of the pion would be living, and suppose that the maximum speed of pion could be speed of light, not more than that. So range covered by the pion would be speed multiplied by time of its life. So time of its life is delta t, and the speed is actually c. So when you multiply both, you get ch by mc square, and it actually boils down to h by mc. And when you calculate that, you get to know that the mass is 275 times the mass of the mass of electron. And when you find the mass of actual pion, it is actually very close to this value. That means Heisenberg's uncertainty principle is very much working for the not theoretical part only, but for the real life scenarios as well. Okay. So how we did this? We just manipulated. We have m is equal to h bar by r naught c, and when you break it down, it is h upon 2 pi r naught c, and you need to just multiply by m naught and m naught, because on one side you will get h by m naught c, and this is nothing but Compton wavelength. And Compton wavelength, we have the predefined formula, and in that way, when you put the value of all the constant, you get it in the multiple of m naught, that is the mass of electron here, and it is 225 times. So this is the established usefulness of the Heisenberg uncertainty principle. So we are done with many important parts and previous year questions of Heisenberg's uncertainty principle. Let us move to the next part.